Hello there. You might have noticed that there's a chapter missing about video mode setup. There is a very good reason to why it is, if only I can remember it. All I know is it's definitely not because I forgot about it. So what we'll do in this video is we'll go over that code in a bit of a code review fashion and try to go into details about what we're doing and why we are doing things. So let us travel back in time. Let's get to it. Oh, right. So it starts here. Right after we have finished loading our memory map from the BIOS. So we have this find video mode sublabel here. And what we're doing here basically is we're calling interrupt 10 with function 4f00. So let's take a look at what the documentation says. So this is the documentation we have for interrupt 10 function 4f, and we are interested in 4f00, which is get super VGA information. So we first start by getting the information about the BIOS video support. By the way, all the links to all documentations are in the reference page on the project GitHub if you want to follow along. Right, so here what we have is to get the VGA or SVGA information, we put 4f00 in AX, we put in ES, so ES is the extra segment, and DI is the DI register. We put a buffer that will get filled with the information, and we call interrupt 10, and as a result of that, we'll have 4f in AL if the function is supported, and we'll have 00 in AH if the query is successful, or 01 if it's failed. And of course, if it is successful, we'll have the buffer pointed to by ESDI filled with the info. And now the only question that we have is, what is the layout of this buffer that we will get back? So let's take a look at that. So here is the layout. So we have a signature on the first 4 bytes. The signature is Visa or for Visa 2.0, which we are interested in. The signature should be VBE2. Then we have a word which is the version. Don't really care about that. We have a pointer to the OEM name. We have some capabilities flags. Then we have a pointer to a list of supported Visa and OEM video modes. And here we are told that it is a list of words terminated with basically -1. And here we have a word that's the total memory or total video memory in 64K blocks. We don't really care about that for now. We're not going to use VB 1.x. We're going to use VB 2.0. So here we get some other OEM software version. We don't care about that. Some other pointers to product name, vendor name, and revisions, stuff like that. And yeah. And after this, basically all the pointers here that are listed here will point to bytes that are listed after the end of this struct. But we don't really care about most of those, so yeah. Let's go back to code. So here you can see that we're doing exactly what we were asked to do in the documentations. We're putting 4f00 in AX. We're putting into DI the address of a temp buffer. Here you can see that our temp buffer is located at 0xb000. And we are putting into the very first D word of that buffer, we're putting in the signature that we want to, basically we are signaling that we want to get info about Visa 2.0. So we're putting VBE2, and then we call in the interrupt 10 we check in that we have in AL for F, signaling that the function is supported, and that we have in AH00 signaling that the query was successful. If we have that, so the compare is equal, we jump to this label here. Otherwise, we just print an error and we panic. Right, so here we are at load mode pointers. The thing we are going to try to do here is, so going back to the documentation we have here at offset 0e, we have a pointer to a list of supported modes. And the pointer, of course, is a D word. So here's what we're gonna do. We are just going to take the D word, gonna put the first half or the lower, I guess, word of it into SI. The upper word, basically E plus 2 is 10 in hex. Put that into AX, and then we are going to increment DI, or basically put into DI the buffer plus 1 sector. So basically we are incrementing the pointer to our buffer. And what we're going to do here is we are going to load items from this list. That's basically pointed to by this pointer here at temp buffer plus E. And if the item that we have loaded, so basically that's what load string word does. We've already seen this before. It reads from SI into AX. So yeah, we compare AX, the value that we've read, with FFFF, which is our termination value. If this is equal, we basically jump over here. If it's not equal, then we OR AX with itself to basically check that AX is not 0. And if it's 0, we still go to this label here. Otherwise, we do store string word. So we basically store the mode value that we've loaded into DI here, this pointer here. And then we increment BX. BX is basically the number of modes that we've read so far. And we keep doing this until we've read all the modes from that pointer, from that list. And the modes are basically just words. So after that, we basically XOR AX with itself. We zero out AX, and we store it to AND that list. So basically what we did here is we transformed the list that the BIOS has passed us, given a pointer here, or rather here, into a list that we stored in DI, in temp buffer plus 200, which is just the modes that we read, and it is 0 terminated here. And of course, we've skipped over all the 0 modes and stuff like that. So now we know that we have a list. I should probably just do, let's put in some comments for now. So at 0xb000, let's do something like this. We have the SVGA info. Then at 0xb200, we have a list of video modes that we basically read from the pointer that we found in the SVGA info. So now what we are going to do next is we are going to loop this list, and for every mode of the list, we are going to query the BIOS about the mode info. And we'll get to that in a bit. Let's first take a look at what the code does, because it's fairly simple. So in SI, we load the address of our list, and in DI we load basically 10 buffer plus 400. So this is basically the next thing here. There we go. So here, this is our new buffer that we've put into DI, and we XOR, basically we zero out EAX. And what we're doing here is we are loading one item, one word from SI with load string word. And basically it loads it into AX. And we're checking that it's not 0 because we know that our list here is 0 terminated, right? And if it's not 0, then we jump forward to this label here. So basically, I don't know if we've went over this mechanic here in fasm, but this here is a sort of anonymous label. So let's say that we have here some label like this. If I use add f, it will jump forwards to this label here, and if I use here add b, it will jump backwards to this label. It's just a way to define labels that can be used in loops and stuff like that without actually giving them names, because we all know that naming stuff is really hard in programming in general. Right, so back to this, we check that we are not at the end of our list, and we jump forward to this label here. Then we move AX into CX, and then we call this, basically we call int 10h with this function here for f01. So let's go and take a look at the documentation. All right, so here we have for f01, super VGA BIOS gets SVGA mode information. So this is the query to get the information about one single mode given its, I guess, ID. So the way it works is we put F or AF01 into AX. In CX, we put the ID of the mode. And then in ESDI, we give it a buffer, a basically 256 byte buffer that will get filled with the mode information. So let's take a look at the mode information that we get back. And as always, the return of these interrupts in AL, we get for F, if the function is supported, we get AH00 if it's successful with the buffer filled. Otherwise, we get 01 if it failed. So yeah, if we go to the mode information here, we can see that we have some very interesting stuff. First of all, we have this thing here, mode attributes. It's a bit field. In bit 0 in the least significant bit of this word, we have basically this bit is set if the mode is present in the hardware configuration. Otherwise, it's clear. In bit 1, we have optional information available. We don't really care about that. In 2, we have BIOS output supported. 3, we have... so basically, 3 is very important. We have 3 set if this is a color mode, if it's a mode that basically manages color or takes in color information, or it's clear if it's just a monochrome mode. 4 is set if it's a graphics mode, and it's clear if it's a text mode. And of course, here we are interested in VBE v2.0. 5 mode is set if the mode is not VGA compatible. We don't really care about that. 6 is set if the bank switch mode is not supported. We don't really care about that. 7 is very important for us. 7 says that the mode is basically supports a linear frame buffer. 8 is all about double scan modes. We don't really care about those. And the rest of these are for VBE v3.0, which is a bit of a flop. All right, so back to SVGA mode information. We've seen the mode attributes. Then we have, so let's just try to go over the important stuff. We have, so at offset 0x10, we have the bytes per scan line. So basically a scan line is the actual width of an actual line on the screen, if I can formulate it like that. And this field here gives us the number of bytes. So basically the actual size in memory of one single line that goes on the screen. Here at offset 12, we have the actual width in pixels of the frame buffer, or if it's a text mode, we have the width in character. 14 is a word that gives us the height in pixels. Here you can notice that we have the width in pixels, but the width in pixels gives us absolutely no information about what the actual size of one line is in memory. That's why we need this field here. Right, so next important thing is probably the memory model type. And here we have a few, so basically the memory model type is at offset 1B. And here we have a few types. We have 0 is for text. We have 01 for CGA graphics. Don't worry about all these. The one that we actually want is 06, which is direct color, also called high color or 24-bit color. And this mode is the mode that we all are familiar with. In this mode, the frame buffer is laid out so that for every pixel that we write, we have to give it the 3 components of color. And every component of color takes 8 bits or 1 byte. That's why it's 24-bit color, which is basically red, green, and blue. Right, so I guess we should also take a look at these fields. So basically, as I said, we are in direct color mode, or actually we'll try to find a mode that supports direct color. But we have no control over how the color components are laid out in memory. So we do not choose how the color components are laid out, the mode does. And the way it does is basically it gives us the offsets of every one of the components. So it tells us that the red field position is so, green field position is so, and blue field position is so. But we don't really need to check all of these to know which fields go where. We just need to check one of them because there are only 4 combinations that can be valid. So yeah, we'll see that when we get to the code. And then here, if we go down to VBE 2.0, the most important stuff here is this pointer here at offset 28, which is our the physical address of our frame buffer. And yeah, that's it. So let's go back to code and see what we did. All right, so here's what we are doing. So we call int 0x10 with this function here for f01. We check that we have actually succeeded. So for f in AL means that the function is supported, and 00 in AH means that the function has succeeded and that the buffer was filled with the information about the mode. And of course here, since we have loaded the mode with load SW, the mode here was loaded into AX, and here we are moving AX into CX. So we are actually loading the mode into CX as it should be. So once basically here we compare this. If it's not equal, we go back to this mode error label. Otherwise, we just continue here and we do some checks. So the checks we do is we basically, so here just to simplify things, temp buffer plus 400 is just our buffer here. So it's just B400. So we can ignore that. And here we have the offsets that I've actually put into, I believe, struct. Yeah, so the offsets that we are checking are these ones, 0, 1b, 19, 12, 14, 10, and 28, and 24. So here we are checking the mode attribute offset. We are loading that offset into AX. And then here we are creating this. So let's just put a bit of space around this. We are creating this, I guess, constant here that's called VB mod flags. And what we are doing here is we are basically stating the flags that we want our mode to have. And these are also defined here. So we want our mode to be supported, which is the bit number 1 or number 0 in our bit field. We want our mode to be of type color. The reason this is set to 8, 116, and 128 is if I go and type in 8 decimal and we look at it as a binary, we can basically see that it's just a bit being set at the 4th position, or bit 3, so 0, 1, 2, 3. And if we go to our documentation about the mode attributes here, we can see that if bit 3 is set, we basically have a mode that supports color. And exactly the same happens with 16. With 16, we set the bit 5. With 128, we set the 8th one. So that's why we have these values. Basically, we are just shifting a 1 by the number of bits that it needs to set. This is basically 1 shifted 3 times, and this one is 1 shifted 4 times. Right, so the modes that we want is we want this to be supported, we want color, we want graphics, and we want a linear frame buffer. So what we do is we take basically the mode attributes, we AND them with the modes that we want, and we compare them to the modes that we want. Basically what the AND does is all the bits that are different between the two will get zeroed out. And if we compare it again with the mode flags that we've computed, we should have the same value, meaning that if the bits that we want remained, this mode contains all the flags that we want. Obviously, if it does not, we go to a label called next mode, which is over here, and we do the loop again. If this one matches, then we go compare the second thing what we need to check. We need to check that the memory model offset, or rather we need to check that the memory model is direct color, and the memory model is at offset 1b. So let's see here, memory offset, yeah, it's 1b. And once we check that again, we compare it to VB direct color, which is what we wanted, with a value of 6. Of course, if it's not equal, we loop again. If it is, then we check that we have a bytes per pixel of 32. So bytes per pixel is the offset 19 in our mode info struct. And the reason that we want 32 is because it lines up nicely in memory. We know that 32 bits is one whole D word, and we know that we can easily manipulate D words. So that's just to make it easier for us. Having 32 bits per pixel means that since we are using only 24 bits for the color, we will have 8 bits or 1 byte basically empty, but that's fine. And here again, we check the width and the height, and we compare them to this variable here that I called required width. And this variable should be somewhere in the bottom here. Yep. So I required a minimum width of 800 and a minimum height of 600. But we can actually choose any values here, and nothing really stops us from changing our video mode to something more or higher resolution if we want afterward. But for now, I just had to choose something, so I put in 800 and 600. Right, so we check the width and height that they are at least equal. So basically, we want them to be above or equal to our required width. Right, so if we have made it here and we didn't loop again, that means that we have found a match. And since we have found a match, then the first thing we need to do before we set ourselves up into that video mode is to fill our boot info struct with that mode's information. So that's exactly what we're doing here. So here we are putting the bytes per scan line field into BX. Then we're moving that into boot info frame buffer scan line. Then here we are putting the width into AX, moving that into frame buffer width. Same for the height, goes into frame buffer height. And the frame buffer physical address goes into FB pointer. And of course here we have, as I said before, we need to figure out the actual pixel format, which is basically the order of the color components. And we have 3 color components, but we have 32 bits, as we asked for that over here. That means that we actually have, we can assume that we have 4 color components with 1 color component not being used, is the general assumption here. And the color component that's not being used, I called A. Usually A means alpha, but here there's no actual transparency, there's no alpha to be managed, so it's just not used. Right, so the actual formats that we can find are RGB or ARGB, RGBA, which is basically just this, but the unused component is at the end. We have ABGR, which is basically RGBA but in reverse, and we have BGRA, which is basically ARGB but in reverse. So we see that the color components only have a few combinations that they can be in. And so what we do here is we just check the blue component's offset. If we are getting told that the blue component's offset is 0, that means that this blue component here should be, of course, we are in Little Indian. So the blue component being the least meaningful byte of the 4 bytes we have. Its offset being 0 means it appears first on memory, and here it should appear last. So if it's 0, meaning that we can only be in this combination here, because this is the only combination of the 4 that has blue at the end as the least meaningful byte. Here, if we are told that the blue component's offset is 8, meaning that it's the second byte to appear, we only have one combination in which this is realized. So it's this one. And if we have the blue, we are told that the blue field's offset is 16. We only have this combination that realizes that. Otherwise, if it's more than 16, if it's 24, then the blue component should be the last byte or the most significant byte. And it only goes in this format. So this is how we decide the format. It's just a quick way that basically lets us avoid having to reconstruct the format from checking the blue field size, the red field size, and the green field size. And with this, we have a video mode selected. We have filled boot info, the boot info struct with our video information. So we just finally need to set ourselves into that video mode. Okay, so here we need to set ourselves into the video mode. So we call inten with this function for f02. Let's take a look at the documentation. Right, so inten function for f02 in AX, into BX we set the video mode ID, but we need to change a few things, or rather one thing. And this one here is for VB 3.0, so we don't really care. And of course, the return would be for F in AL if it's supported, and 00 in AH if it's successful. So the thing that we need to change is there is an actual bit field here in BX that's expected, and bit 14 for VBE 2.0 plus. If it's set, we use the linear frame buffer, and this is something that we want to use, so we should set bit 14. So what we're doing is we are taking from CX the video mode, because it was last put into CX since we've used it to call into this function here to get the mode info. We put that into BX, and then we use BTS, which is byte set, to set the 14th byte. It's bit set to set the 14th bit. And then we move for F02 into AX. We call our interrupt, and we check that we have succeeded here. And if we did, we jump forward to this anonymous label. Otherwise, we just print an error and we panic. Well, that is how we set up video modes. Hope you liked that. Hope it was fun. Let me know in the comments if you liked the format. Like, subscribe. See ya. Bye.